Today we are going to do some exercises connected with magnetic field. And first of all, we have to define magnetic fields of two different systems. The first system is a straight lone wire with current. It looks like this. With electric current. Our purpose is to find magnetic field that is produced by this current. First of all, it is necessary to define magnetic field lines, form of lines of magnetic field. And I think we can do this. By right-hand rule, and we can do this from symmetry. What about symmetry? It means that magnetic field always has the same symmetry as the system that produced this magnetic field. So what type of symmetry has this system? Can you define this type of symmetry?
Sure. I have a little question. Now we are discuss the practice. Yes, the exercise.
Yes, and
the electricity and magnetism exercises, right?
Electromagnetism, yes.
Sorry, teacher, I don't understand which question do we discuss.
Which question? We have a straight lone wire with electric current, and it is necessary to find magnetic field around this wire.
Number variant. What's the which variant of the exercise do you discuss?
It is without number. Because there is no this exercise. This exercise.
Okay.
Maybe I will type this. Is to find magnetic induction. Magnetic induction B. This is the question. And now it is necessary. The first step is to define symmetry. Is to define symmetry of this system. Maybe you can remember from electrostatics that there are 3 types of symmetry in our exercises. 3 types: plane of symmetry, axis of symmetry, and center of symmetry. So it can be plane, axis, or center. Plane, axis, or center of symmetry. Center of symmetry. For example, if we have ball has center of symmetry. Ball. For example, cylinder has axis of symmetry. Okay, and what about this system? Okay, this is definitely axis. This is definitely axis, and it means that magnetic field produced by this system, magnetic field, has the same symmetry. Magnetic field has the same symmetry. Okay, so let's draw this. Let's draw this. It can be drawn. Line of magnetic field can be drawn in this way. This is a magnetic field around a straight long wire. Around straight long wire. Around a straight long wire. So this is magnetic field, but I'll make here dash line. Dash line is a part of the line, part of magnetic field that is behind the screen. That is behind of the screen. And here this is a part of line that is between us and the screen. Okay, the next question is how to find the direction of magnetic field. Direction may be this or this, or this, and we have to choose the correct direction. We have to choose the correct direction.
Use right hand rules. Right hand rules. Yes.
Right hand rule, of course, yes.
Yes.
Yes, yes, this is correct. This is correct. Right hand rule. Right hand rule allows us to define the right direction of magnetic field. Yes, this is correct. This is correct. So we have defined the direction of magnetic field. Direction of magnetic field. Yes. I'll remind that how to use right hand rule. According to this rule, if this right hand these fingers shows the direction of magnetic field, and this finger shows the direction of electric current. So electric current is here, and direction of magnetic field is here. This is right hand rule. Okay, this is correct. And let's draw radius of this line. Radius is here. R. Radius is here. Radius is here, and the next step is to find the modulus. To find the modulus of vector B, modulus of magnetic induction. Modulus of magnetic induction, and there are two ways. To define this. There are two ways. Maybe you can remember at least one of them. Okay, these
You
ways.
find what, teacher?
Yes.
To find what?
To find B, the modulus of this vector. Yes, this vector. This is correct formula. This is correct formula, but this formula requires to know H. Requires to know H, but we don't know this. We don't know this. Okay, this is good. This is Biot-Savart law. Biot-Savart law. Yes, we can use this. We can use this, but we need. I think we need another form of this. This form is for magnetic field of moving charge. For moving charge. But we need to use Biot-Savart law for electric current. For electric current, and I'll remind this. Mu 0 divided by 4p electric current cross product dl multiplied by r divided by r to the power of 3. Yes, it can be used. This can be used to define magnetic field. But it is quite a difficult way to do this. We have another way. That is simpler in this case. And this way is to use Ampere's circuital law. I'll remind this. Ampere's circuital law. Linear integral of B dl is equal to mu 0 mu and mu 0 sum of circuits plus mu 0 mu 0 square integral area inside closed loop L, partial derivative of electric displacement vector multiplied by ds. Multiplied by ds. So we have two ways. To define magnetic induction B. We have two ways, and it is the second is more simple. To use, and we have to take into account, first of all, we will use this, and we have to take into account that according to the condition, there is no electric field. And because of this, because of absence of electric field, we can we can put it as 0. This is 0 because there is no electric field. According to the condition, we have only electric current, not electric field. Okay, but to use Ampere's circuital law, to use this, we have to find integral in the left side of the formula, and we have to find this. We have to find this. Let's calculate the integral in left part. Let's calculate the integral. Let's calculate the integral. The first step to do this is to define, is to choose loop L. The first way is to choose the loop L, and the best way to do this is to choose this loop the same as green line. Let's do this. Let's define. Let's choose L the same as green line, the same as line of magnetic field B. The same as line of magnetic field. In this case, we will obtain that B has the same direction as DL, and because of this, dot product or scalar product B and DL is equal to B DL multiplied by cosine, and what angle do we have here? Zero. Yes, it is definitely equal to 0. It is definitely equal to 0. Okay. This is 0. This is 0. So we have this is equal to B D L. B D L. This is equal to B D L. Okay. 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 And according to this, we have that this is equal to B L B D L, and this is equal to I'll remind that we have chosen L the same as this green line, the same as line of magnetic field, and because of this, B modulus of vector B doesn't depend on DL, DL, and because of this we can write B outside the integral. outside the integral dl. And this integral is very simple to calculate. Very simple to calculate. Very simple to calculate. This is length. This is length of circle. Length of the circle with radius r. With radius r. So we have 2p r multiplied by b. 2p r multiplied by b. Multiplied by b. Okay. Do you have any question about this?
Yes.
Yes. No questions.
I don't catch how to get this.
This is length of because we have chosen green line. We have chosen line of magnetic field. That is green line. We have chosen this we can chosen this as loop L. Loop L, and this integral is this integral. This is the same as sum of all elements dl. This is sum of all elements dl. All elements. And dl this is a little part of this circle. This is dl. This is dl. And because of this, we have that this is equal to 2p r. Okay, do you have any more questions?
No, thank you.
Okay. Okay. Okay, the second is the second step is to define the right side of Ampere's circuital law. Sum of electric currents. Sum of electric currents. And this is all electric currents. All electric currents that passes inside loop L. That passes through L. What do we have here? According to the picture. According to the picture. It is necessary to have a look at the picture and to find all currents that passes inside closed loop L. Okay, but I think we have only one current. We have only one current. This current. This current. We have only one current, and because of this, all that we have is to write this current here, because because we don't have any more currents. We don't have any more currents in our system, and the green line is loop L, is closed loop, and the current I is passes through this through area that is bounded by loop L. Okay, so we have find left side, right side, and now we can use this. So we have 2p r multiplied by b, and this is equal. This is equal to this is equal to mu 0 I, mu 0 I, and because of this we have that b is equal to mu 0 I divided by 2p r divided by 2p r. Okay, do you have any questions about this? No questions. No questions. Okay, so I will clear some unnecessary things from the screen. I'll clean this. I'll clean this, and we have found that magnetic field of this current is mu 0 I divided by 2p r divided by 2p r. Divided by 2p r. Divided by 2p r. Okay, do you have any questions about this? No questions. No questions. In next exercises, in future we can use this formula. We can use this formula without any proof, because we have already proved this. So we can use it. Okay, I will clean this. And the next exercise exercise is to find magnetic field of solenoid. Magnetic field inside solenoid, and I will look at a perfect solenoid. Perfect solenoid. Or inductor, or induction coil, induction coil. We have spoke something about this yesterday, as you can remember, and we used formula for magnetic field inside this, without any proof, and now the question is to prove this formula. So we have solenoid. Solenoid is a wire that has form that is similar to a spring. We have electric current here. Perfect means that B outside the solenoid, BE. Magnetic field outside the solenoid is equal to 0. But there is magnetic field. Inside the solenoid. And magnetic field inside the solenoid is homogeneous. Magnetic field inside the solenoid is homogeneous. And the question is to find vector B. The question is the same as it was in previous exercise. So the length of solenoid is equal to L. It has n turns. So with n turns. And we can make a signation. Something like linear concentration of turns. Is equal to number of turns divided by the length of solenoid. Okay, so here we have we also have two ways to define this. And both of them may be used. but this way will be very difficult to use because we will obtain we will have to calculate quite difficult integral, and it is possible to do. It is possible to do, but it may take us very long time to do this. So let's choose the second way. Ampere's circuital law. Ampere's circuital law. We will use the second way. In this case, we also don't have electric field, so we can write this. So we can suppose that this add is equal to 0. This is Maxwell's addition. This add is Maxwell's addition, and this is connected with electric field, and in this case, this is equal to 0. This is equal to 0. Okay. Okay. So how to find the left and the right sides of this formula? The first of all, it is necessary to choose closed loop. To choose closed loop L. I will draw one more picture that is the same. I will draw one more picture. I'll draw one more picture for us, and I think that it will be useful. It will be useful to choose closed circuit as this rectangle. Let's choose this closed loop. So this is L. This is L. And we have 4 parts. 1, 2, 3, 4. This length is equal. This length is equal to L. This length is equal to L. This length is equal to L. Okay. And so what do we have here? We have that integral b dl is equal to integral integral from 1 to 2, integral on side 1, 2, B D L plus integral 2 3 B dl plus integral 3 4 B dl and plus integral B dl for 1 for 1 for 1. Okay. Okay, so do you have any questions? No questions. Okay, and so we have to find these four integrals. These four integrals. And okay, what can you say? What can you say about magnetic field? Magnetic field on part 3, 4. What about magnetic field? Magnetic field on part 3, 4. What can you say about magnetic field? Okay, external magnetic field, according to the condition, is equal to 0. External magnetic field is equal to 0. Is equal to 0. And because of this, we have 0 here. Because of this, we have 0. Oh, no, not here. Sorry. Not here. This is here. 3, 4. This is 0. Okay. Do you have any questions about this? Do you have any questions? No questions.
Why 3, 2, 4 is 0?
1, 3, 2. And I don't understand.
Why this equal to 0?
Why this is equal to 0? Because magnetic field is equal to 0. Integral of 0. Integral of 0 function is always equal to 0. Because we have external magnetic field is equal to 0. And this leads to 0 in integral.
Why only this side? Why only 3, 2, 4 this side?
Only in this side, because we still don't find other integrals. I think we will do this now.
Okay.
Okay, so I will clean some I will clean some things. I will clean some things from the screen. Oi. I will clean some things. And okay, the next step. The next step is to find the integral on part 2, 3. Okay, and as we can remember, here we have magnetic field. Here we have magnetic field. Here we have magnetic field that can be shown like this. So here we have vector B. Here we have vector B. Okay, so so what can you say? What can you say about angle? About angle between B and DL on this part? Angle between B and DL on this part 2, 3. We can see that this is right angle. This is right angle because here B has right angle with DL. B has right angle with DL, and because of this, we have that B DL is equal to B DL cosine cosine of 0. Cosine of the no 0, sorry, 90 degrees. 90 degrees. 90 degrees, and it is 0. It is 0. So because of this we have 0 here. We have 0 here. But the same situation is for part 1. Here we also have B perpendicular to DL. B is perpendicular to DL, and because of this we have 0 for this integral. Okay, do you have any more questions? And do you have any more questions? No questions. Okay. Okay, so let's clean some place. Let's clean some place on the screen. Let's clean some place. Let's clean some place. And So all that we have is the last integral on part 1, 2 b dl and in this case what angle between b and dl do we have according to the picture? So for this case we have that b has the same direction as dl, and because of this we have that b dl is equal to b dl multiplied by cosine 0, and this is b dl. This is b dl. This is b dl. So we can use this integral on linear. This is linear integral on part 1, 2 b dl, and we have that magnetic field inside the solenoid is homogeneous. This is homogeneous, and because of this we have that we can write b outside the integral. And this integral is simple length of part 1, 2. This is length of part 1, 2. So we have obtained b multiplied by l. Okay, do you have any questions about this?
No.
Okay. Okay. So I will clean something. From the screen. I will clean something, and the second step. The third step. The first was to choose closed loop L. The second was to calculate the right side, and the last step, the third last step is to find the right side of Ampere's circuital law. This sum. And how to find this? In this case, we have n turns. We have coil with n turns. So we can write that this is equal to n multiplied by current in one turn. So now we can substitute our results to Ampere's circuital law, and from this we have that B L is equal to mu mu 0 n I. And from this we have that B is equal to mu 0 n divided by L I, and this is mu 0 n I. Okay, so do you have any questions? No. No. Okay, that's great. That's great. I will clean some things from the screen. I will clean some things from the screen. So we have proved this formula. We have proved this formula that we used yesterday. Yesterday we used this formula without proof, and now we have proved this. Now we have proved this. So we can frame this, but from yesterday you already have this formula in red frame. So this is answer. This is the answer to this exercise. So I hope we have learned how to use Ampere's circuital law to define magnetic field, and let's try to do the exercise number 17. The exercise number 17. Exercise number 17. The exercise number 17. Exercise number 17. A coil with current I, was placed in homogeneous magnetic field in such way that its axis coincided with the direction of the field. The winding of the coil is one layer and made of copper wire of diameter d. And the radius of turns r. Radius of turns r. At what value of internal magnetic induction the winding of the coil may be broken. Okay, and it is necessary to add one condition. To add tensile strengths when copper breaks. This critical critical tensile strength. I'll think I will sign this like sigma C, sigma C, sigma critical, this critical tensile strength when Cooper breaks. So we have coil. The turns of coil are rings, and let's draw one of these rings on picture. Let's draw one of these rings. Let's draw one of these rings. Let's draw one of these rings. There is current in this ring. There is current in this ring, and this ring is in internal magnetic field. It is in internal magnetic field. B. The direction of magnetic field according to the condition is the same as the direction of the axis of the coil. And we have to find the force that is impressed on this ring from magnetic field. How to find this? How to find force? How to find force that acts on electric current in magnetic field? How can we find force that acts on electric current in magnetic field? I think we can use
Left hand rule.
Yes,
Left hand rule.
left hand rule. Okay, I agree. We will use this. But we will do it a little bit later. We will do it a little bit later. Now, we are interested in remembering formula to define this force. I think we can use Ampere's force law. Ampere's force law. According to this law, D F A, Ampere's force, is equal to electric current multiplied by vector product I dl multiplied by vector B. Multiplied by vector B. Multiplied by vector B. Multiplied by vector B. So let's define the element of the circuit dl, the element of conductor dl. I'll draw diameter of this turn. I'll draw diameter and I will define the element of this ring in this way. So we have that E. This will be alpha, angle alpha, and this will be D alpha, and this is D L. This is DL. Okay, and we can use left hand rule to define the direction of this force. What is direction of this force according to the left hand rule? We can use this left hand rule. According to this, we have left hand here. The vector B is directed to the palm of left hand. So here we have vector B directed to the palm. These fingers show vector DL, and thumb, the last finger, thumb, shows us the direction of Ampere's force. Shows us the direction of Ampere's force. Okay, so do you have any questions about this? No questions. No questions. Okay. Okay. So I'll clean this. I'll clean this in order to have some place on the picture. In order to have some place, and so the force DFA is directed here. Is directed here. Okay, let's find the modulus. Let's find the modulus of Ampere's force. Let's find the modulus. DFA is equal to the modulus of DFA vector vector, and this is modulus of this vector product. B dl b, and this is equal to E B dl E B dl multiplied by sinus. And what angle do we have here? What angle do we have here? Angle between vectors B and dl. Yes, 90 degrees. This is 90 degrees. Yes, I agree. This is 90 degrees. 90 degrees. So it means that 90 degrees. And because of this, we have that this is equal to E B dl. E B dl. Here, so we have found the modulus of Ampere's force, but we still cannot integrate this. We cannot do this. Why? Because dfa is a vector. This is vector. And because of this, we cannot integrate this. Because the modulus of sum of two vectors, isn't equal to the modulus isn't equal to sum of moduluses of vectors. So this is not the same. So if we integrate here, we will obtain something like the right side of this formula, but we need left side. So we have to do something with this before calculating integral. And the way what do we have to do? We have to define some direction. We have to set a coordinate axis. And to find a projection of vector dfa on this axis. So we have axis x. And how to find projection of vector dfa on axis x. How to find this? I mean I mean this. I'll show this separately. So this is the axis x. This is axis x, and this is vector. This is vector dfa. This is vector dfa. This is vector dfa, and here I will draw a dash line. I'll draw dash line. Dash line. Dash line. This is alpha. This is alpha. This is right angle, and this and this is df. This is df. So how to find df from this picture? How to find this? Yes, this is dfa multiplied by sinus of alpha. Sinus of alpha, but without vector above dfa, without vector. Okay, this is correct. This is correct. So we have that this is equal to I b sinus alpha dl. But we still cannot integrate this. We still cannot integrate, but because we doesn't know the dependence between alpha and dl. But it is easy. It is easy to find this. The radius of the turn is r. So because of this, we have that dl is equal to r multiplied by d alpha. So we have that this is equal to I b r sinus alpha. Oh, sorry, sinus alpha d alpha. Sinus alpha d alpha. And because of this, we have that this we can integrate. That force, tensile force. This is tensile force. This tensile force is equal to integral from 0 to f df, and this is equal to integral we have to take half of the ring, so we have integral limits from 0 to p I b r sinus alpha d alpha sinus alpha d alpha, and this is equal to I b IBR integral from 0 to p sinus alpha d alpha, and this is equal to minus I b r cosine alpha from 0 to p minus I b r minus I b r cosine p minus cosine 0, and this is equal to minus I b r multiplied by minus 1, and this is 2 I b r 2 I b r. So we have obtained that tensile force is equal to 2 I b r 2 I b r. Okay, and what about tensile strengths, critical tensile strengths? This will be equal to F divided by square of cross section of the wire, square of cross section, and we also have 2 here. Why do we have this? We have this because the tensile force is distributed between two sides of the ring, here and here. Diameter has two ends, and because of this we have 2 in denominator. So according to our results, we have that this is equal to 2 I b r divided by 2. And what about square of cross section? Square of cross section will be p diameter of cross section to the power of 2 divided by 4. This is square of cross section of the wire. 2 I b r divided by p d to the power of 2. To the power of 2. So b is equal to p d to the power of 2 sigma critical divided by 2 IR. 2 IR. Okay, do you have I have
Teacher, how?
made
Oh,
a
yes.
mistake. A little mistake. A little mistake. We have 4 here. 4. Okay, do you have any questions? No questions. Okay, so the next homework is number 16. Number 16. The next homework is number 16. Number 16. So, okay, if you don't have any more questions, thank you for your attention. Thank you for your attention. I hope to see you next week.
See you, teacher. Have a nice day.
Have a nice day.